Good morning, Professor. We are P7-Team 2, and today we are presenting our traffic simulation abstract engine. Our goal was to architect a generic, robust, and scalable framework capable of powering any 2D simulation, be it a traffic sim, a platformer, or a physics sandbox without any modification. Let's first look at the high-level architecture. We enforced a strict unidirectional dependency. As shown in our package diagram on the left, the engine package is completely decoupled from the logic package. The engine manages the data and execution flow, while the logic layer injects specific behaviors. We also adopted a manager-centralized design, where the scene manager acts as the central state machine and orchestrator, communicating between application, abstract, and libgdx. We've also wrapped all libgdx calls behind interfaces to ensure our architecture isn't tightly coupled to the libgdx framework. Building on this manager-centralized design, the engine is powered by 5 core managers. First, the scene manager. It uses a stack-based architecture with an array deck, which allows us to push overlays, like a pause screen, on top of the active simulation without unloading it. Second, the entity manager. We prioritize thread safety here, using copy on a write array list to ensure that spawning or destroying entities during the update loop never causes a concurrent modification exception. Third, the collision manager. This handles axis-aligned bounding box collision detection and physics resolution only, pushing entities apart. It deliberately does not know about game rules like scoring or sound effects. It separates the pure math of hitting a wall from the gameplay of what happens when you actually hit it. Fourth, the movement manager. This adheres to interface segregation. It operates on any object implementing the movable interface. This decouples physics calculations based on entity type. And finally, the input manager, which uses the observer pattern to broadcast input events to multiple subscribers.
Hi, my name is Aung and I'll be talking about our additional managers. The I/O manager handles file and JSON serialization. It uses Java's optional string to process file reads, which prevents runtime exceptions if a map or save state is missing or corrupted. This ensures safer data persistence and asset loading. The sound manager is responsible for audio resource management. To optimize for performance, it caches sound objects into a hash map. This prevents the overhead of reloading audio from the disk during simulation, which is important for maintaining a stable frame rate during high activity sequences. Finally, the time manager wraps libgdx delta time calculation. This allows the engine to remain framerate independent while also enabling future extensions for slow motion, fast forwarding, or pausing using time scaling. The engine's execution follows a frame lifecycle to ensure simulation accuracy and visual consistency. The process begins with the input phase. Hardware events are processed first, so the simulation can immediately account for user input. This is followed by the update phase, where the entities can modify their internal states such as velocity. The physics phase occurs after movement. This sequence allows the collision manager to detect overlaps and apply displacement vectors before the frame is rendered. This prevents issues like entity rendering inside walls or tunneling through objects. Finally, the render phase sorts entities by their z-index before drawing them. This ensures correct visual layering, so background objects are drawn behind foreground elements.
Hi, I'm Joel and I'll be taking over the slides for OP principles. We applied OP principles in a way that keeps the engine reusable and hard to break. For abstraction, abstract entity defines what the engine expects from any entity, such as bounds and a random method, without forcing one specific implementation. At the system level, scenes can call collision processing without needing to understand the underlying AABB math. For encapsulation, we focus on protecting internal state. It's not just getters and setters. Entity Manager exposes an unmodifiable view of the entity list and uses defensive handling when needed, so external code can't accidentally mutate the engine's core data structures during runtime. We use inheritance and polymorphism to keep the engine consistent and easy to extend. With inheritance, shared entity behavior like ID position, bounds updates, and z-index live in abstract entity, while static entity and dynamic entity only implement what differs. For polymorphism, manager work with interfaces like movable and iCollidable, so any entity that implements them automatically plugs into movement or collision without changing manager code. For Liskov substitution principle, any subclass of abstract entity can replace the base type in the engine pipeline safely, because it preserves the same update and render contract expected by Entity Manager and the render loop.
Hi, I'm Isa and I'll be walking you through how we handle collision logic and how we make sure that it actually works. This slide illustrates our most critical decision, logic injection. The engine knows physics, but it shouldn't know game rules like play a crash sound. As shown in the activity diagram, the engine first checks all entity pairs for axis-aligned bounding box overlap. When overlap is detected, it resolves the physics by calculating the minimum translation vector and pushing entities apart. Then it triggers the collision listener. The listener is the bridge. The logic layer injects a lambda function that defines game-specific behavior. In our case, it checks impact speed and plays a crash sound when thresholds are exceeded. The engine handles physics. The application decides when to play a sound. This strategy pattern keeps the physics engine pure and the game logic completely separate. An engine is useless if it's fragile. We approach testing in two ways. First, visual testing. As shown in the table, we verify edge cases like dragging a car into a wall and spanning cars inside walls, confirming the engine auto-ejects them correctly onto the first frame. Second, headless integration testing. We build an automated test suite that runs without a graphics window, making it consistent and reproducible. As the table shows, it validates high-speed collisions preventing tunneling and, more importantly, test fault tolerance. Adding null entities or removing non-existent IDs logs warnings rather than crashing the application. This mimics industry-standard reliability practices.
Hi, I'm Zayne, and I'll be going through the UML diagram. Firstly, our abstract engine utilizes composition over inheritance. The abstract scene composes managers, allowing for modularity when swapping managers and mock testing. By composing managers inside the scene, we control their life cycle. When a scene is popped from the stack, the managers die with it. This prevents the common singleton pollution. Moving on, using aggregation between abstract entity and the collision listener allows for collision behavior to be attached dynamically at runtime for all entities. By holding a reference to this listener, collision listener, the engine allows the application layer to inject gameplay logic such as playing a crash sound or updating the score at runtime. This keeps our abstract engine pure and the logic remains flexible. And lastly, using interface-based dependencies, we achieve a strict application of the dependency inversion principle. The movement manager does not know what a dynamic entity is. It only cares about the movable interface, as you can see here. For example, we can add a bolt or a particle as long as they implement the movable interface, and the physics engine will work without needing to change the abstract engine.
Finally, I'm Joseph and I'll be taking the conclusion and demo. Let's jump straight into the demo. So firstly, let's launch the visual stimulation. We start in the menu scene. The scene manager is currently running the menu logic. When I press enter, this pops the menu and pushes the simulation scene, loading our world from a JSON file via the IO manager. When I right-click to spawn entities, the entity manager adds these to a thread safe list, inheriting properties from abstract entity. As I drag and release a car, this demonstrates the input manager, thereby triggering the movement manager to apply a velocity vector and frame-based friction. Watch this collision. The engine resolves the physics, but additional actions or effects, like the car crash sound, is triggered via the collision listener interface. This keeps the engine pure and demonstrates logic injection. Notice even if I try to force a car inside a static wall, the collision manager continuously resolves the conflict, pushing it out. When I press escape, the scene manager pushes a pause overlay onto the stack. The simulation scene is still frozen in the background. When I press escape again, the entities move, proving our stack-based architecture. Finally, for persistence, when I press F5 to serialize the current state to the IO manager, and then I mess up the scene. And finally, I press F9 to deserialize and restore the state. As I dynamically resize, the engine automatically recenters the UI and clamps entities to new boundaries without breaking physics. Next, let's jump into our headless integration test suite. This runs the core engine loop without graphics context, hence the term headless. As you can see, the engine passes all the integration tests for movement manager, collision manager, and we have a few fault tolerance or edge case tests. As I conclude, trafficking has achieved our objectives of creating a strictly decoupled abstract engine. Our engine is scalable and reliable, as proven via our automated headless tests as part of our testing methodology. This concludes the trafficking demo.